So morning everyone. Welcome to the course. So I'm just going to give a very brief introduction to the ARCHER2 training program. This training is provided as part of the ARCHER2 service. What is ARCHER2? Well, ARCHER is the UK National Supercomputer Service. It's managed by UK Research Council, EPSRC, but the machine is housed, operated and supported by EPCC. And the hardware is supplied by HPE. Now, actually, this course, although we're running on ARCHER2, doesn't have ARCHER2 in the title because hopefully almost everything you'll learn today will be generally applicable to a wide range of parallel machines. But as part of running the ARCHER2 service, we provide training about 60 days per year at various locations. It used to be mainly, well, obviously during COVID, it was mainly online, but we're transitioning back to being more face-to-face courses. And these courses are free to all academics. At least the online courses are. We may charge for commercial attendees at the face-to-face courses. ARCHER2 is this Cray Shasta system located at the EPCC's ACF, the Advanced Computing Facility. That's an artist's impression. This is what it really looked like. That's a picture of the initial system a few years ago, but it's nice because the back is off and you can see all the wires. This is the current system you're running on today. Hopefully you'll all have guest accounts on that machine. We also have a machine called Cirrus, which we use for other courses. It's a tier 2 system, but we're not using that today. So, I mean, maybe you know what EPCC is, but EPCC is the closest thing that the UK has to a national supercomputer centre. We've been around since 1990. Originally called the Edinburgh Parallel Computing Centre, but we're now just EPCC. And we're a self-funding centre at the University of Edinburgh. We've been running parallel systems for a long time, since the first national parallel system back in '94, which is also was a Cray system, a Cray T3D. There's over 100 people now, and we do a range of academic commercial projects. And part of that is postgraduate teaching and HPC training courses. And so the reason I mention this is, you know, if you go away from this course and you think, well, that's well and good, but I'd like to work with EPCC, a lot of our staff are basically research associates. We act like RAs on research grants. So a lot of our staff work full or part-time collaboratively on joint research proposals as research assistants. His Pitch of Edinburgh, it's an online course. It doesn't look like this today. It's pouring with rain here, but unfortunately, yeah, well, not this is an online course, obviously, but that's where we're in Edinburgh. There's some ARCHER2 resources here, but they're not actually that relevant for this course. Everything's shrink wrapped in the online documentation, so I'll skip over that. Who am I? I should introduce myself. My name is David Henty. I'm in charge of education and training programs at EPCC as a whole. That involves our on-campus MSc programs and online as well. Courses on the ARCHER2 training program and some commercial trading. My research interests are in sort of parallel programming models, performance, and parallel I/O. Please fill in the feedback form. Claire will send you a link at the end of the course. We do take feedback seriously. It's all considered. We review all the feedback at regular meetings. Good feedback is great. It makes us feel good about ourselves. But also critical feedback is equally important because we will act on it and try and improve the courses. And that form is anonymous if you want it to be. Just plugging our own course training here. We run a couple of one-year MSc programs, postgraduate master's programs, the MSc in HPC and a stream with data science. That's been running for over 20 years. And we now have online versions as well. This is a graduating class from quite a long time ago, actually. We typically now have about 40 or 50 students on the on-campus program, and maybe 20 or 30 joining every year on the online program, but it was a lot smaller in the past. Other training material you might be interested in, maybe not for yourself, but for your colleagues who might want to learn about. We started up a very an open course, a MOOC, massively open online course under FutureLearn, which is the online arm of the Open University. And that's still running you can join it for free. They try and get you to pay, but you don't have to pay. And it's completely conceptual, no computer programming required. And it now runs in a self-study mode. But that course is up there. And you know, if you had colleagues who were interested in learning the basics of HPC, that's maybe a good place to start. During the course, you'll have these personal accounts for the duration of the course, and you'll have access for about up to a month afterwards. After the access ends, all your files will be deleted. So if you do have work that you've done, please take copies. That's probably not so relevant for this course because we're just running a couple of shrink-wrapped applications. But the most important thing is that don't worry about the course materials. All the material will continue to be available from the ARCHER2 website, along with recordings. I'll just double check I am recording this session because I often forget to. Yes, I'm recording. So the recordings will go up shortly afterwards as well. Longer term, if you want to, if you're not an ARCHER2 user, you've already got an account for a training course, there's various ways to apply for time. These all require some kind of justification of resources as far as you maybe a full research application. But you can get pump priming access, which is the lowest barrier. But actually, if you just want time on ARCHER2 to test things out, you can take the driving test. It's quite a simple online test. And if you pass that test, you get 800 compute units for up to 12 months. A compute unit is a node hour. That's actually quite a lot of CPU time, and it's there to bridge this gap between. You'll not get access to a big project on ARCHER2 if you can't prove you can use ARCHER2. But how can you prove you can use ARCHER2 if you don't have access? And that breaks that cycle there. This isn't relevant. We're training online. There's a code of conduct, just in general. If you have any, that's there. You can look at it. And there is, if you have any concerns about anything on the course, behavior of either any of the trainees or the attendees, then you're welcome to report it. There's an instant reporting form there. Also, we run these regular funding calls. Again, if you go away from this course, think, oh, that's great, I'd like to improve the I/O of my code, and I don't know how to do it, or I don't have time to do it. There's a thing called Embedded Computational Science and Engineering Support, the ECSE program, and this funds research software engineers to carry out software development of ARCHER2 software. But that's recently been expanded to look to the future, to anything preparing for exascale. So that encompasses GPU work as well, looking forward. Just very briefly, we're not. I mean, the exact hardware setup of ARCHER2 isn't particularly relevant for this course, but I mean, we're really interested in the I/O, the way the disks are arranged, which I will cover. But ARCHER's sort of about 6,000 nodes, each with 128 CPU cores. That's about 750,000 cores. It's quite a large machine. It's purely CPU. There are no GPUs in ARCHER2. Standard access via slow and batch system. Something which is slightly confusing, there are two file systems. Every user has a home and a work directory, and you'll start off in home, but you have to run from work. And again, I put that in the instructions. I recommend you CD straight to work every time you log in. And for today, we will have reserved queues for fast turnaround. So I've set up the submission system so that your job should run very quickly. And I hope you enjoy the course. And please ask questions. As I said, the material will be up there for reference for forever, effectively, and a recording of the lectures. So I'd rather spend the time we have today face to face, or at least virtually face to face, answering things you want to know about, rather than going over stuff which is written down and maybe isn't so interesting to you. So that's really just a very brief. If any of you missed any of that talk, that was not really that was just a message from our sponsors, effectively. I just briefly want to go over the resource, so this is the ARCHER2 training page. And if we look at upcoming training, you'll see this course, which is Efficient Parallel I/O. And if you go there, this is the splash page. And here is I'll try and stick to the largely to the timetable. There's time for lectures and exercises, and we'll actually finish by about 3:30, but then I'll be back for half an hour after the break to answer any questions or finish the exercise. It gives us a bit of slack. But also the course materials here goes to a GitHub page, and that is where you can access all the material, which is I've linked in the lectures here, and also the Okay, that's something else. The exercise sheet and a link. So just that's the main page. If you go to the training page, you can find the parallel IO page. This is our standard advertisement, general advert for the course, but for this specific course, the course materials are linked here. Again, they'll stay up there on GitHub under our EPCC Ed. So that's all I had to say. I was just going to give the first lecture now, which is really a general overview of what the challenges of parallel IO are. Then I'll talk a bit about how Lustre, the parallel file system, works on ARCHER2, and then we'll get started before the break. And the main reason for having a practical before the first coffee break is just to make sure that people can log on, and we'll carry on afterwards and see how things are going. So if anyone does anyone have any questions just before I start? Stop sharing. Let me just check. Give me a second. I'm just having this slight issue getting hold of the many windows to cope with. Okay, so the first talk I'm going to give is really just going to outline what the challenges of parallel IO are. In some sense, why are we giving this course? So hopefully you can see that slide there. Okay. So I'm going to talk a bit about what the challenges of parallel IO are in general, and these are things to keep thinking about for the whole of the course, really. If you have any questions, easiest if you just ask them in chat, and if you ask them in chat, I get a notification, so I'll pick up any of your questions as we go along. So what this lecture is going to cover is sort of why IO is difficult in any, just as a topic, why it always causes problems, why parallel IO is even more difficult, and an overview of what kind of solutions people tend to use, some of them rather ad hoc potentially. What is parallel IO trying to achieve? What would we actually like to do? And then a very brief discussion of files as arrays and MPI-IO. Now, this course was originally a sort of 1.5, 2-day course on MPI-IO. You can do parallel IO as part of the MPI standard, and that's what this course originally was. But it turned out that people were more generally interested in parallel IO as a general topic. And so I changed the course around, and I don't give anywhere near as much detail on MPI-IO, but I will give a small amount of detail because understanding MPI-IO is a very good way of understanding parallel IO in general, and I'll explain why later on. So why is IO hard? Well, you know, whenever you run, you have a computer and you run programs, you run PowerPoint, you run Firefox or whatever, you have this nice process, you know, very ring-fenced processes, each with their own memory. Everything's very virtualized in some sense. But when you do I/O, the data in memory has to physically appear on an external device. There's some spinning disk somewhere, possibly a long way away, and the data actually has to physically appear on that device. And why is that harder than memory? Well, files are very restrictive compared to data arrays. You know, if you have data in memory, you can access it, you know, as an array. Random access is easy, but random access in a file is very difficult. If you're continually seeking through the file, it's very inefficient. And so to get, we'll come back to this, but to get, you know, good I/O performance, you really want to do linear access. You want to just, you know, sweep through a file from start to beginning and write it in order. But linear access to the file may require remapping of the program data. Your data in memory may not be stored in a contiguous and linear way. So you may have to do some manipulation to transpose or rearrange your data so it fits nicely in a file. So that's kind of nasty. There's many, if you look at any system, there's lots of system-specific options to IO calls. It can be very, very non-portable. There's loads of different formats. We'll talk a bit about HDF5, NetCDF later on. There's a new one called ARCHER2. You can have text and binary. If you're using binary, then if you have floating point numbers, they can be stored big endian or little endian. The 4 bytes or 8 bytes can be a different order. Fortran unformatted access is just horrific. That's from a software side. Disk systems themselves are very, very complicated. An individual disk may actually be a cluster of disks, a redundant array of always inexpensive array. I mean, disks are very complicated. They can actually be multiple disks. There can be lots of caching on disk in memory. For example, by default in Linux, if you write a file to disk, it doesn't go to disk at all. It's cached in memory, and such on. And so it's really, really nasty. I think I/O is the HPC equivalent of printing. You buy a new laptop, you plug it in, you switch it on, everything's great, everything works, but then you try and print a file, and you have the data from your laptop has to appear on an external physical device, and it's just a complete nightmare printing. I did actually have a quick poll. I just wanted to basically ask people have a little poll. So I'm just interested if people, hopefully you can see that. I'm just interested. Now, we're not going to do any bespoke programming in this course. I'm going to give you a test example. It looks like if people could just answer the, it's just useful to know. Okay. So we basically have most people 2 to 1 are C, C++, and about 2/3 C, C++, and 1/3 Fortran. That's interesting to know. Now, for historical reasons, the test code I'm giving out is actually a Fortran code. That's purely historical. It doesn't actually affect how you do parallel I/O, but that's useful to know. Thanks very much. Okay. So I'm going to do a very, very simple example here, but which is in C, but it does illustrate the challenges of parallel I/O. So imagine you've got a 4x4 array, double X44, and we want to write it to disk. Well, of course, we know that in C, or in any language, C or Fortran, if we have a 2D array of size 4x4, what we really get is 16 elements arranged, and there's some mapping from these 16 elements, 1, 2 to 16, to the 2D array. Whether it's C or Fortran, you can, whether it's stored row major or column major, it doesn't really matter for the example. But so what we have is we have a 4x4 array, and it has 16 elements, 1, 2, 3, 4, up to 16. Now I've colored these for later reference, but this is just just think of a serial program. How do I write, if I had a 4x4 array in a serial program, how could I write it to file? Well, I could open a file pointer, and I could write X, and its size of 16 doubles. And it would be the same in very similar in Fortran. You would use system write call. And what would happen is that data will be written, the array X would be written to file, and it would be written linearly to file. So it would be written in the order 1, 2, 3, 4, up to 16. So you would get a file on disk of size 16 times size of 888, which is 128 bytes long, and the 16 elements will be arranged linearly in that file. So the interesting thing to note there is that if you just do a naive write of an array to file, then on file there's no memory of that being coming from a 2D array. That you'd have to encode that in metadata, at least in C and Fortran. Okay, but now we're going to do parallel I/O of a 4x4 distributed array. So we don't have a 4x4 array, we have a 4x4 distributed array, and we've decided that we're going to split this 4x4 array across 4 processes: process 1, process 2, process 3, process 4. So I now have a very simple decomposition of my parallel data onto a 2D grid of processes. And of course, in the distributed memory model, in message passing MPI, what actually happens is there is no 4x4 array. Okay, that's purely fictitious in your head. What you actually have is each process has a little 2x2 array, and that's why I have colored them to match up to this. This is how we're going to distribute the bottom left-hand corner to the yellow process, that to the blue, that to the green, that to the red process. Now, what I would like to do, we'll come back to this, is I'd like to write the data out to file in the same order as in the serial file. And the way I've just drawn these arrays, that means that I go up the way. So it's yellow, it's 1, 2, 3, 4, 5, 6, 7, 8. I would like the data array, ideally, I would like the file I produce on disk to be the same in parallel as it is in serial. And so that means it's element 1, 2 from the yellow process, 1, 2 from the blue process, 3, 4, 4, 3, 4, 2, 3. Okay, so if I think that the data is contiguous in this direction, the way I've drawn it here, I have a magic parallel I/O call here. So each of the 4 processes has a 2x2 array, but there are 4 processes in the 2x2 grid, which makes up this global 4x4 array. And you can immediately see that even this almost completely trivial example, a 4x4 array distributed across 4 processes, the data pattern is actually quite complicated. Okay, this part of the array comes from the yellow process, this here blue. There's quite a complex interleaving of data from the processes to the file, and that will turn out to be one of the major problems with parallel I/O. It's quite a complex transformation of the data on each process to the data in the file. And so we will look at ways to do this later on. But this illustrates the issue, and this is for almost the most simple problem you can imagine. If you have much more complicated problems, 3D arrays, unstructured grids, it gets even more complicated. But even this simple example illustrates the point. So what do people actually do to try and do this? Well, the first thing they do is you might think that we could just all open the same file. So what you might think is, okay, what we'll do is each of the 4 MPI processes will declare a file pointer and it will open some file. Okay, so all the 4 processes are opening the same file on disk. Okay? And then each process is just doing lots of it. This process is the blue process. Well, I need to seek to here and then write, then seek to here and write. The red process needs to seek to here, right? So each process is just, they're all opening the same file, skipping, writing all the way through. Okay, that looks like it might work. Now, first of all, this will not work in general, because multiple processes writing the same file is problematic. We'll discuss what problematic means. But definitely on a standard Unix file system, this is not going to work. Also, the performance would be very poor, because to write the data, each process I'm going to do a write, a seek, a write, a seek, a write, a seek, a write, a seek, a write. And as I've mentioned before, file systems are not optimized for that. They don't like lots of little access. What you want to do is write 100 gigabytes of data to disk. And so, but why won't this work in principle? Well, it's because of the way that, so why is parallel I/O harder? Okay. Well, we can't generally have multiple processes writing to a single file. Linux generally can't cope with this. And this is because of the way that data is cached. I've got a diagram to illustrate this next here. You might think, well, surely it's okay because these processes are all writing to distinct parts of the file, okay? But that is not actually in general the case. This will not work even if each process writes to a distinct. There's clearly a problem if 2 processes write to the same part of the file. There's a clash there. But even if each process writes to a distinct part of the file, in general, that won't work. That's on a standard Unix file system. A parallel file system may get the right results, but it would get the right results by locking the I/O. So a parallel file system is aware of the fact that it could have multiple processes writing to a single file. Unix in general isn't aware of that. But what it might do is it might just lock the file, and this will completely serialize the I/O, and so you'll get very poor performance. So the next slide illustrates why, in principle, this seek write is not a good thing to do. You might say, well, clearly reading is okay. Surely 1024 processes can open a file and read it. The problem is that this can overload a file system. If you open the same file 1,000 times, then the file system can just they're not built for that. They can't cope. So that's the problem with the file system. The other problem is just, in fact, the major problem about parallel I/O is that data is distributed across different processes, and processes do not in general own contiguous chunks of the file. This is not colored yellow, blue, green, red. The yellow data, the blue data, the green data, and the red data from the different processes are interleaved in relatively complex ways. So you cannot easily do linear writes. You can't just say write lots of data. And in fact, even more complicated, in a parallel program, your local data may have halos, which is effectively junk data, which may have to be stripped off. So there's just a whole bunch of things which make parallel I/O harder. But I just wanted to illustrate in principle why simultaneous access to a file is a problem. And the reason is that well, access to memory is appallingly slow on modern computers. Why is your laptop quite fast? Well, because we have cache memory. And so because writing to memory is slow, we avoid writing to it. When we write data, if we can, we write it to a much faster but smaller piece of cache memory. That's the same. That's the way that operating systems work with I/O. When you write to disk, writing to disk is slow, so they don't write to disk. They write to a cache, and that cache is just stored in memory. So when you open a file and write to it, what probably happens is the data is cached in memory and will later on be flushed to the file when you close it, for example. So why does that give us a problem? Well, it gives us a problem because Unix file systems, these default ones, don't understand that they could be accessed by multiple processes at once. So imagine I've got a file here, and I've got process 1 wants to access the first half of the file, and process 2 wants to access the second half of the file. So what process 1 does is, now files are stored in disk blocks. Okay? So when you store a file, it's actually the minimum size a file can take up on disk is a disk block, and a standard file system has disk blocks of 4 kilobytes. This is the file equivalent of cache lines for memory, but a disk block is something like 4 kilobytes long, or could be bigger on a very large system. So if I open a file which is only 1 byte long, it occupies a whole disk block. A disk block is the minimum transaction you can do with a disk. When you ask for data from a disk, what you get is a whole disk block at once. So this file occupies 3 disk blocks. It might be 12K long. So when process 1 wants to read this file, okay, what it does is in memory there will be a disk cache. So process 1 says I want to read this first half of the file, okay. The operating system will say, well that encompasses the first 2 disk blocks. So I will cache in memory the first 2 disk blocks. And like also process 2 has its own cache, because process 2 is in a separate process, potentially on a completely different computer, and it has its own disk cache. So when you ask to read this data, process 1 gets a copy of the first 2 disk blocks in its disk cache, and process 2 gets a copy of the next 2 disk blocks in its disk cache. And then process 1 gets the data in memory, and process 2 gets its data in memory. So everything seems fine. Then process 1 alters the data, and process 2 alters the data. Okay. And then later on, you might decide to write it so you decide to write that data to disk. Okay, so you open the file and you write it to disk. But what the operating system does is it says, well, I'm not going to write to disk. That's very slow. I'll just stick it in the disk cache. Okay, so you've opened the file, you've written it, or you've updated your disk cache, and you've updated this. Someone else has updated their disk cache. However, somewhere down the line, this data is actually going to have to appear on file. Maybe when you close the file, maybe when your process ends, maybe when you log off, and who knows. But at some point, this data is actually have to end up on disk. So what happens, unfortunately, is what process 1 does, it just flushes its disk cache to file. It does that. Process 2 flushes its disk cache to file, but process 2 doesn't understand that another process has actually updated the file. And so you get a clash, that you get junk data here, because the file system the file system sets up multiple disk caches, or the operating system sets up multiple disk caches, but these disk caches, unlike memory caches, are not coherent. That's because, when was Unix written? 50 years ago. Okay, so I mean, a standard Unix file system is not designed to be parallel, so it doesn't understand that it could be accessed by multiple processes at once. And so even two processes accessing different areas, writing to different areas of the same file, can cause a problem. So that's maybe a bit of an aside, but that's the first. So this naive solution number 1, which is everyone opens the file, you do seek write from multiple processes to a global file, is not going to work. So what do people do next? Well, the next thing people do is they say, I will do independent I/O, or file per process. Each process opens its own data file and writes its local data. Now, this is simple to implement, but in my opinion, is a total nightmare to cope with, because the biggest problem we have, why parallel I/O is becoming such an issue, is that parallel computers are becoming very, very large. ARCHER2 has 750,000 CPU cores. An MPI program on ARCHER2 could have hundreds of thousands of processes. So what you do is you end up with this file per process approach. You write potentially thousands or hundreds of thousands of files, and that requires a lot of pre and post processing. When you run your program, you have thousands of files, and that's really very difficult to cope with. The data format depends on the number of processes. Okay, so you'll get, if you run the same program on 10 processes or 20 processes, you get 10 files or 20 files, so that you get completely different output from the serial code. So with this file per process approach, unless you do quite a lot of post-processing to munge all these data files back together again, you get a different, and I find this philosophically wrong. I think parallel computing should get the same result but faster. I don't think so. This, although what a lot of people do, is conceptually simple to implement, and all you do is you say, okay, everybody opens a local file and everyone writes their local data to the local file. So if you, in this case, we get 4 files, data1.dat, data2.dat, data3.dat, and data4.dat. And later down the line, if you wanted to recreate this big file, you'd have to stitch these back together in some way. So what we really want to achieve is to have parallel data like this, but to have the same files we had in serial, a single file, at least logically a single file, which is numbered, which has all the data in the correct order. The naive solution number 3 is called controller I/O, and what you do there is you send all the data to or from a single controller process. So what you could do is you could basically, for writing, you could gather all the data from all the processes to rank 0 in an MPI program and read or write a single file. So all you would do in this example here, sorry, the animations, is you would basically process 1 would gather all the data from all the other processes into a big array and write it out. Now that's good because the main advantage is that the output is the same as the serial. So this does give you that your parallel program produces the same file as the serial program, and it's a single file. The issues is, A, you quickly run out of memory on the controller, because in a real parallel program, there's no way the entire data set can be stored on a single process. So you end up having to write in many small chunks, which can be a bit of a coordination nightmare. But we'll see later that the real problem for this is the performance is poor. Only a single process is writing. This is a serial solution, and this gives you no benefit from the parallel file system, which we'll see later. We'll see that large computers like ARCHER2 have parallel file systems, and we'll cover what this means later on. But if you do a serial solution like this, you have a single process. The parallel file systems require multiple processes writing at once to get good performance, and this is a serial solution. So it's still relatively simple to implement in practice, but will give you poor performance. So what we need is a way to do parallel I/O properly. We want the I/O system to deal with all the system specifics. We want to ideally end up with a single file format, which is the same as the serial format. I would like the file I produce from my parallel program to be in the same format, the same layout as the serial file. All files should have the same. So yeah, the data should be the entries should be stored according to the position of the global array, not depending on which process happened to own them. And there are a number of libraries which do this. MPI-IO, the ones I'll talk about today are MPI-IO, mainly HDF5, NetCDF, and ARCHER2, but we'll consider MPI-IO first. So what we need, and the reason I'll consider MPI-IO is A, I understand it the best for historical reasons, but B, MPI-IO is used at the bottom level by a lot of other parallel I/O libraries. And if you understand how MPI-IO works, you have a good understanding in general terms of how other parallel I/O libraries work. So what you need, what the system needs, is you need some way to tell the I/O system that this data is split up in this form, that this data is split up in this form. You need to tell the I/O library what the mapping from the local data is to the global file. So the problem is that mapping is in the mind of the programmer. Okay, your computer, your file system has no idea that we think these processes are arranged in a 2D grid. So we need to describe the data. We need to have an extra. This is the critical extra step in parallel I/O. You open a file, you write the data, and you close the file. But before you write the data, in any I/O library, parallel I/O library, there's a way of describing the data layout to the I/O system. And that's how most of these I/O libraries differ. It's how you do that description. But this is the crucial step in all parallel I/O. Tell the I/O library what portions of the global file each process owns. And so therefore, I'm saying, although you think of you're running a parallel program on 4 processes, each of which owns a small part of a distributed 2D array, in reality, the computer is just running 4 processes, each of which has an array of size 4. And that mapping is in your mind. You have to tell the I/O library explicitly what that mapping is. And so the way that a lot of I/O libraries work, and definitely MPI-IO does, is that you think of a file as a large array. Okay? Forget the I/O actually goes to disk. Imagine we are doing controller I/O, that we're recreating a single large array on a controller process. What you do is you tell the I/O library how each subsection of your distributed array fits into this larger array. Now, the I/O system then creates this array and saves it to disk, but it does it in a clever way. So although sort of logically you're doing controller I/O, you're telling the I/O library where each section fits into this global array. The global array never exists, otherwise it would run out of memory. So what you want the I/O system to do is to write this data, but without running out of memory, so never actually creating the entire array. You also want to do a small number of large I/O operations. You do not want the I/O library to say, okay, the yellow data goes here, so I'll write that data and that data, the blue data goes here. You want the I/O library to be clever and say, well, actually, David's told me where this yellow and blue data lives. That means that this yellow and blue data together form a large, big chunk. What you want the I/O library to do, and this is the art of getting good parallel I/O, is to enable the I/O library to aggregate this data together and do a single big write, not lots and lots of small writes. So data aggregation before actually writing to file is a key step of performance. And so, sorry, I've jumped to the wrong place in the slide. Apologies about that. We wanted to merge data to write large contiguous sections at a time. And we also wanted to use any parallel features, okay? We'll see that parallel file systems have multiple I/O nodes. You want your library to do that automatically, and also to manage any coherence issues around these files, any clashes, such like. So we'll come back to these concepts later on, but as I said, the main point at this stage is there's this extra step in any parallel library where you describe the layout of the local data to the parallel data. How does MPI-IO does that? Well, MPI-IO is part of the MPI standard, and as each process needs to describe what subsection of the global array it holds. And MPI-IO does that using MPI data types. So in MPI, basically, what you do in it, if you want to do parallel I/O and MPI-IO, at some stage, process 3 has to tell the I/O library that it owns the bottom right-hand corner of this large 2D array, and it does that by defining an MPI-derived data type, which is a 2x2 subsection of 4x4 array. And there are a lot of standard MPI-derived data types you could use here. You could use vectors or subarrays if you're familiar with that. But that's the way that MPI. So this stage, this crucial stage of describing what subsection of the global array each process owns in MPI-IO is done using MPI-derived types. Now, there are lots of other parallel I/O libraries. We'll talk a bit about, very briefly, HDF5, NetCDF, and ARCHER2 today. But MPI-IO is usually the lowest level, even though you may not call it directly. So if you call the HDF5 parallel HDF5, it will call MPI-IO somewhere lower down. And the approach is the same. Each of these libraries will have some way of describing what portions of the file each process owns. And actually, they typically use MPI-IO to do their reads and writes. So that's why I think MPI-IO is useful to look at it in a bit more detail, because it underlies all these other libraries. And all these libraries work effectively language neutral. They work C, C++, Fortran. So summary, parallel I/O is difficult in theory and in practice. MPI-IO provides a higher level of abstraction where you basically imagine you have access to a single shared file between all the processes, but it's up to you, the programmer, to describe the mapping from the local to the global data. And MPI-IO hides all the system-specific details, but takes advantage of them. And we'll see what a parallel file system can give us to give good I/O later on. There are lots of more flexible formats that have more metadata and are more easier to use, NetCDF, HDF5, and ARCHER2, but they all layer on top of MPI-IO. And MPI-IO requires a good understanding of derived data types. That's not so crucial now that on this course I don't cover MPI-IO in any particular detail, but that's how it works. So that's the end of the first lecture. That was hopefully just a general. It would be useful to have this example in the back of your head. Although it's ridiculously simple, this 2x2 array, and the benchmark I will run is effectively, that we will run today, is effectively this setup, but it's not a 2D array, it's a 3D array, and it's much bigger. But this is the problem we're going to solve, and so that's the first lecture there. Does anyone have any questions? What I will do is I have too many windows here as ever. So we're sort of on time. What we're going to do is going to give a brief overview of the Lustre file system on ARCHER2, but importantly, that is modulo details is going to be the same as almost any parallel file system you'll encounter. And then before the break, and around the break, we'll do our first practical, which I put around the break, because if people have login problems, we can solve them over the break. So I'll take a 5-minute break now and just get a glass of water. But I will be back. Say 10:22. Get myself a glass of water. But I'll back in 5 minutes. So the question is lack of. So as I'm not an expert on, but my understanding is that a standard file system like you get on your laptop will not keep the cache coherent. That's my understanding. It would be very expensive to do it. Cache coherency is I mean, the simple way to do it is just the simple way to get around the coherency problem is just to lock every time you open a file and write to it, to lock that file. And that's the default behavior of a parallel file system. But that's a good question. I don't know. It isn't. My understanding is that a standard Linux file system will not maintain coherency between the disk caches, and actually maintaining coherency will be a very, very complicated problem. I mean, cache coherency in memory systems is incredibly complicated to do efficiently. I should do an experiment actually to see if this, but I think what the reason for that slide was really to show. Often people think, surely it will work if each process writes to a different section of the file, and that is not guaranteed to work. It might work in some cases, but not guaranteed to work because of this cache coherency issue. But I apologize, I'm not an expert on the details. This is, of course, why you should never pull a USB stick out of a laptop without closing it, because you've written a file, and you think you've written the file to the USB stick, but it probably hasn't gone to the USB stick. It's probably cached in memory. So when you close down elegantly, the system realizes to flush. It needs to flush the data to an external drive. Okay, so I'll now get the next lecture. So what we're going to talk about now is parallel file systems and Lustre. Lustre is the actual parallel file system that we use on ARCHER2, but it's pretty universal now. So most parallel computers you come across will use Lustre. Even if they don't, these concepts are fairly general across parallel file systems. So we used to have a system a while back which was an IBM system that uses GPFS. It used GPFS, general parallel file system, and the concepts were all the same. The terminology was different, but the concepts were all the same. So what I'm going to cover is what is a parallel file system, how does Lustre work, striping, which is the key concept in parallel I/O, and some very, very simple Lustre commands which you can play around with when you get onto ARCHER2. And I'll just have a few diagrams to illustrate, given this design of a parallel file system, what are the possible bottlenecks? What's going to slow you down when you write to file? So I don't. Lustre will take out the kernel. I don't know what you mean by taking out the kernel. Sorry, that I don't. I mean, well, actually, we'll come back to how. Well, I'm not really okay. That's interesting. We can discuss it. Right. So, right. What is a parallel computer? Right? Well, a parallel computer it's often a surprise to people, but for the last couple of decades, at least, parallel computers are constructed of many standard processors, each not particularly fast. You buy lots of fairly cheap processors. And why do you get performance? Well, the performance comes from using many processors at once. Okay, so the clock speed of the processors on ARCHER2 are probably slower than the clock speed of the processor on your laptop, but we have hundreds of thousands of them. And what's the downside of that? The performance comes from using many processors at once. It requires you, the user, to manually distribute data and calculation across processors. You have to write a parallel program to take advantage of that. So by analogy, what's a parallel file system? Well, again, a parallel file system is constructed from many standard disks, each not particularly fast. Okay, you don't buy a super fast disk, you buy lots of standard disks. So how do we get performance? The performance comes from reading or writing to many disks at once. So we'll see that the way you get fast parallel I/O is to write data to lots of disks at the same time. Now, the way that the file system works is you have the file system has lots of clients. So when I say, so what we want is lots of clients, lots of processes accessing the file system and reading and writing to different disks. And the way, just for reference, the way that it typically works is that each HPC node appears as a separate I/O client. So you know, these parallel file systems may not have been initially developed for parallel computing. They might be developed to have you know, single disk system across many workstations. But the way that to the Lustre file system, what does ARCHER2 look like? ARCHER2 looks like about 6,000 individual computers, each of which is a client doing I/O. But the way that we can get parallelism, we'll come back to this later in the lecture, is that data from a single file can be striped across many disks. So you're going to have a file system which has lots of disks. So files are going to be distributed across lots and lots of different disks. It's going to be quite complicated. How do you know where the file is? When you do ls or ls-l, you want to just see a single file, even if in practice it's split across lots of disks. Well, the file system must appear as a single file system to the user. So we have a single database which remembers all this stuff. And this is in Lustre, it's called the metadata server, the MDS. And so in Lustre, you have a single metadata server, but lots of disks underneath controlling lots of disks. So the MDS is the metadata server, which gives the illusion of there being a single, as the files are just stored as normally on a single disk. So in Lustre, the parallel file system looks like this. Is a diagram from Cray, I think. We have the application process running on the compute nodes. We have lots of application processes. And fundamentally, we have lots of disks. Now, Lustre calls them OSTs, object storage targets. Okay? And they may in themselves be RAID arrays, which is they're actually multiple disks. But I will call them disks because I'm not a hardware expert. But you know, to me, each of these, an OST is the minimum thing you can access. So what I'm trying to say is, I think of the OST, which in Lustre terms stands for object storage target, as actually being a disk. Okay, so you have lots and lots of OSTs. Okay, now in practice, these are actually grouped together. You have object storage servers which control lots of different OSTs. So there's a hierarchy here, but it turns out I think it's much simpler if you just think about OSTs. Okay. We also have a metadata server, a single metadata server, which is in practice lives on a single stores on a single device. But I find it simplest to talk about the metadata server, the MDS, but lots of OSTs, because these are the things you actually interact with directly. Okay. So how does the data get from these processes to these OSTs? Well, what it does is it, first of all, there's a network. You have a high-speed network on any parallel computer which can take this data. That's then shuffled to the OSSs, which then write to the OST. So there's a lot of, you know, there's memory here, there's a network, there's a server here, it is very complicated. But, you know, fundamentally, I think of a parallel file system in lots of disks, which Lustre calls OSTs, controlled by a single database, which Lustre calls the metadata server. Okay? So this is a useful diagram, but the OSTs are the important thing. This is actually a picture. Now, I didn't have decent pictures of ARCHER2, but on our ARCHER, we had these very nice IO systems. So what happens is you have Cray in those days told you something called a scalable storage unit, but this had multiple OSSs, okay? And the OSS is an object storage server, which is basically a computer, a desktop, a server, each with multiple OSTs, each with multiple disks, and you stuck them all together into a rack. So this rack here will have hundreds and hundreds and hundreds of disk units in it. So that you have a huge number of physical disks. Oops. In your system. But terminology said Lustre's got this many different levels of virtualization, but as I said, one object storage server has multiple object storage targets. But I think, and I said a single OST has multiple physical disks, so it's a redundant array of inexpensive disks. So a single storage unit, an OST, might have 10 disks in it, 8 disks and a couple of parity disks or something like that. But I think, the simplest way to think about it is metadata server is the database that contains the information on where a file is stored, and the object storage target is the physical device that stores your data. And I will also call this a disk, although it actually contains multiple hard drives, because the user interacts with the MDS and the OSTs. These are the things that we actually interact with. So how is ARCHER2 actually set up? Well, so you have a slight quandary here, is that you want as many OSTs as possible to get parallelism. The more OSTs you have, the more disks you have in your file system. However, they're controlled by single MDS. So if you have too many disks, this becomes a bottleneck. Okay, so you want as many of these as possible, but without this being a bottleneck. So what we do in ARCHER2 is we have a balance. We have 36 OSTs, but they're split into 3 separate file systems: work1, work2, and work3, each with its own MDS. So actually each project, and we are TA128 is the training project for this course, is assigned to a single one of these file systems. I don't know which one it is, I could find out. And that means that we have access to 12 OSTs and 1 MDS. If we had more MDSs, if we had more work file systems, they each have fewer OSTs. But if we had one big file system, they'd all share the same metadata server, and that could easily become a bottleneck. So multiple file systems means the MDS is less likely to be overloaded. There is also a file system with solid state disks, NVMe, non-volatile memory, not spinning disks. Okay, and we do have access for this course. So you can try the exercises out. This is the first time in this course this is the first run of this course we've had access to the SSD. The NVMe, non-volatile memory. So these are not spinning disks. They're actually just solid state devices. And again, the reason that these were bought is we expect them to be better latency, good for small IO transactions, better for random access, because you don't have a physical disk head moving around. They may also yield better bandwidth. For the purposes of this course, one of the reasons why they're useful is that if you're looking for performance data, you possibly get more reproducible performance data from the SSD system, the NVMe system, because it has fewer users, and so you'll have less contention for the resources. So again, it might be welcome to run your exercises there. The total is we have around 3.3 petabytes of storage. So each file system has around 3.3 petabytes of storage, and that gives us about 13.2 petabytes of data, which is quite large. I'm being pedantic. I'm not normally pedantic, but this is storage in terms of 2 to the power of this. People get a bit blasé when they say kilobyte or megabyte. When they say kilobyte, they mean 1,000 bytes or 1,024 bytes. Well, this is the power of 2 notation. This is the power of 10. There's not much difference between a kilobyte and a kibibyte, but there's a big difference between, it's about a 10% difference between the power of 2 notation and the power of 10. So have to try and be careful about that. So when I say petabytes, I'm actually saying, I can't even remember what the word correctly is pronounced that, but this is the power of 2. Technically, that means that's the power of 10 storage, power of 10 notation. So what's the default configuration? By default, This isn't guaranteed to be the default, but it's the default almost all systems. When you create a file, by default, it will be stored on a single OST. Okay, so when you create a file, it will be the Lustre will decide to put it on a single OST, but it automatically distributes the load across available OSTs to balance the load. So if we go back to this diagram here, if this process opens a file, it might be stuck on this OST. If this process opens a file, it might be stuck on that OST. And so already you do get benefit from parallelism because what we'll see that because the operating system, or at least Lustre, automatically distributes the files across different OSTs to balance the load, and that also gives you parallel access. Now this is called an unstriped file. We'll see that the way that you get better access to performance for accessing a single file is called striping. That's where a single file is split across multiple OSTs. By default, on most systems, when you create a file, it will be unstriped, means it's stored on a single OST. However, reading and writing from multiple files from multiple nodes can benefit from multiple OSTs because we're using different disks. However, access to a single file will not benefit from the parallel nature of the file system. So if you just use standard Linux open and close system calls for doing your I/O, the performance of a single open read, write, close section will not benefit from a parallel file system. However, if you have lots of them going on at once, you will benefit. But the important point is that access to a single file will not benefit from the parallel nature of the file system because it's just stored on a single disk, which is slow. So how do you get better performance for a single file? Well, Lustre has a concept of striping, and in striping, the parallel performance comes from striping single files over multiple OSTs. So you have a single logical file. If you do ls-l on it, you'll just see a big file. But if you ask, and this is under the user control, if you say I want this file to be striped, the file system divides the file into stripes if requested by the user. So a single file is stored across multiple disks. So this is something that you can choose to do, and it's typically what you do for large files is you ask them for them to be striped. So a single file is stored across multiple disks, split across them. And the stripes are therefore read written to from their assigned OST. So if you read and write large amounts of data, you get increased bandwidth because you're actually reading and writing from lots of different disks at the same time. So striping allows multiple I/O processes to access the same file, and it increases the bandwidth you're accessing multiple OSTs. Now, I should have said this before, but typically all these things act to optimize for bandwidth, not latency. The operating system, the file system assumes that eventually you're going to be writing multiple gigabytes, terabytes of data, and so this increases the latency. There's more. If you want to read some data now, you have to say I want to read some data from the file. Whereas it's that data, then that means it's stored on that disk. There's a whole lot of extra steps to go through, so it tends to increase the latency. So this doesn't increase the performance of reading and writing small amounts of data. Reading and writing small amounts of data can be very inefficient. But so parallel file systems are really optimized for bandwidth, not for latency. This is called striping, and the striping of a file is fixed when it's created under the control of the user. And the fundamental parameters are the number of stripes and the stripe size. So if I create a file with a stripe count of 4, so I say I want my file to be stored across 1, 2, 3, 4 OSTs, what the operating system does is Lustre will assign 4 OSTs, let's say OST 1, 2, 3, and 4, but then it will split the file up in a round robin way. So the first megabyte is stored on OST 1, the second on OST 2, the third on OST 3, the fourth on OST 4, back to OST 1. The reason why it's not efficient to split the file up in a block way, which is sort of what this implies, is if I split the file across 4 OSTs, if I read the first quarter of the file, I'm only accessing a single OST. I don't benefit from the parallelism. If I do this round robin and split the first quarter of the file in 1 megabyte slices across all the OSTs, even if I read a relatively small piece of the file, I'm getting parallel I/O because I'm reading from multiple OSTs. And so this is called striping, and this is so this default. So it's a round robin policy of the file is distributed across all the OSTs, and there's a stripe size, and the default stripe size tends to be a megabyte. But the two parameters which define the striping of a file is the number of stripes and the stripe size. And we typically change the number of stripes. We typically use the stripe size as its default, but that's just. So how do you set the so by default a file will be striped across one OST or a stripe count of 1. Well, you can set the striping on a directory of file by using the Lustre file system LFS set stripe -c end stripe on a directory of file. So you actually say, I find it much easier to set the striping on a directory. So I set the striping on a directory, and all the files which are subsequently created in that directory inherit those striping. So LFS set stripe minus the stripe count on the directory of the file. If you say -1, that is full striping. So if you say -c -1, it will stripe it across all the available OSTs, which is 12 on the disk file systems. You can also set the stripe size with LFS set stripe -s stripe size. However, to be honest, we can experiment with this later, but the default tends to be quite good. Now, this does not alter the striping for existing files. Okay, if you change the striping of a directory, it doesn't automatically change. It only affects files when they're created. So if you want to change the striping of an existing file, you have to do a copy. If you're ever interested, LFS get stripe will give you the striping information on a file. So parallel I/O to a stripe file is very complicated. Where in the file does the local data need to be written? Which OSTs are the stripes located on? Are there any write conflicts from different processes? Well, you need to use a parallel I/O library. So that's what we're going to talk about. But looking at this diagram, I think the important point is where the bottleneck is going to be. Okay, are the bottlenecks getting the data off of the processes? Are the bottlenecks in rearranging the data through the network? Are the bottlenecks in writing the data to the disk? Okay, and I've got an analogy here, which I think is a useful analogy. It is a train analogy. So, okay. My analogy with trains, each of these carriages of the train is a node. Okay, so in ARCHER2 there'd be 5,960 of these. Each carriage is a client of the I/O system. Okay, each carriage is a node. Okay, we actually want to write to disks. We want everyone to the analogy is we've got a train drawn up at a platform, and so the carriages of the train are the nodes of the parallel computer. The people are the data, and we want the people to leave the platform through various doors. So the analogy is that the train is our computer, each carriage is a node, one of our multi-core nodes, which each of these is a client of the operating system, and our disks are represented by these doors that we want people to get out of. So we've got lots of people, lots of data flowing out of these nodes. They're all being rearranged on the platform because, of course, people have to go different, and they're leaving the exit doors out here. So getting people from a train out to the exit doors is like writing, in my view, writing data to disk. And if you think about this analogy, where could you get bottlenecks? Well, the first bottleneck is a serial exit door. Okay, it doesn't matter how many carriages you have or how big your platform. If you have a serial exit door, one exit door to your train station, that's the bottleneck, and that's the equivalent of having an unstriped of having your data stored on a single disk. Okay? If all your data is stored on a single disk, it doesn't matter how quickly you can get it out of your carriages, out of the nodes. That's going to be the bottleneck. So writing all the data to a single to a file stored on a single disk is, in this analogy, the same thing as only having one exit door to your platform. Okay? So that if you only have one exit door to your platform, that is clearly going to that's going to be the bottleneck. People will be able to leave the carriages really quickly. They'll all mill around on the platform, but they'll not be able to leave the platform because they're throttled by this single exit door. You might have a serial train door. You might say, well, I've got a big platform and lots of exit doors, okay, but I've only got one way of getting out of the train. And that is the same thing as doing controller I/O. That is saying, you know, I can have a very fast network. I can have lots of parallel disks, okay, lots of exit routes from my platform. But if I only have if I do all the I/O from a single process on a single node, if I only open one door on one of the carriages, it's it's getting the data off of the computer is going to be the bottleneck. So here it's people they're all going to have to run through the train to leave this single exit door. So that's clearly the bottleneck there. Okay, so we don't want to have a single exit from the platform. We don't want to have a single exit from the train. We want to have multiple exits from the train. So this looks like a good thing to do. Here we're letting people off in parallel from every carriage, and they're leaving the platform through lots and lots of doors. So that looks nice. We've got a nice match there between people leaving here and leaving here. But the problem might be, what happens if we don't? What happens if people still capture? What happens if the rate at which people can leave these doors is faster than they can leave these doors? If we don't open enough train doors, okay, then we're not saturating the bandwidth of these exit doors down here. And so actually what you might want to do is, you might say this is good, but actually what we really want to do is to have multiple exit doors, okay? On each of our carriages, we want to open more than one door, because the bandwidth through a single door of the carriage is less than the bandwidth through a single door out of the platform. And this happens if this is the same thing as having more than one process writing per I/O node, more than one process writing per node. And so that's the options here. Okay, this is what we want to happen. We want to have lots of people leaving the train carriages or leaving the doors. Our bottlenecks might be the doors, which is serial I/O, which is I/O to a single disk. It might be leaving the train, which is where we have the equivalent of controller I/O, or it might be, although we have parallel I/O, we're not saturating the bandwidth because we're not got enough doors open on each carriage. So I hope that's the analogy I have in my mind. Hopefully it's useful to you as to what's going on here. But the important point is that there can be a number of bottlenecks in the system, and depending on the system, depending on what kind of I/O you're doing, these bottlenecks can appear at different layers. So the obvious question you have is, does the MDS become overloaded with large numbers of files? If I open thousands of files, can the MDS cope? You might say, what's the maximum performance for a single OST? Can one process saturate an OST? Okay, if one process can saturate an OST, then we can just open the equivalent of opening one door on each train carriage. Can a node saturate an OST? Is the network the limiting factor? How well? To cope with all these to answer all these questions, I wrote a very simple benchmark a long time ago to help investigate originally Lustre performance characteristics and bottlenecks. And so this is called Bench.io. It's up on GitHub, and what it does is it writes a large distributed 3D array of double precision numbers. And it's up there. We'll use this example, but I wrote it really as a way of trying to understand what the bottlenecks were in a real system. It started out as being a project to improve the I/O of someone's cellular automaton model. That's why it's a 3D grid, because this guy Anton had a 3D cellular automaton. That's why it's written in Fortran, because he was writing a Fortran code. This was the paper but I wrote him a simple parallel MPI-IO library to do parallel I/O of a large 3D distributed array, and then generalize that to use other I/O libraries. Before we go on to the exercises, performance variability, you share HPC resource with all users on the machine. On a machine like ARCHER2, you always get given a whole node. So you never share the processes on a node, but you share the network bandwidth with people. And so the same program run twice on ARCHER2 can run at different speeds, because there may or may not be contention on the network. As well as network bandwidth, unfortunately, when you're doing I/O benchmarking, you share access to the OSTs, because you may be using the same disk as someone else. Remember, there's only of order 40 OSTs, and there's hundreds of users. And also access to the MDS. You share the I/O resources with all the same MDS. So all of these can suffer from contention. And so I/O performance can be very variable. And what you typically see is you get reasonable performance. Every now and again, you can get terrible performance. So benchmarking I/O is a challenge because it can be so variable. So summary, a Lustre file system has multiple OSTs, and I think of these as being multiple disks. Maybe more complicated than that, but that's why I like thinking about them. By default in ARCHER2, and it's true on most systems, each file is stored on a single OST. That's called an unstriped file, or a file with a stripe count of 1. However, that benefits performance for multiple files, which can happen from a single user writing multiple files, or multiple users each writing to a single file. Although you share the Lustre file system of the users, if you are writing to a different OST from another user, you're not contending for access to that OST. So there's already some benefits for parallelism, even for unstriped files. However, if we want to perform the access, improve the access, the performance for reading or writing to a single file, that file needs to be, because we only have one file, that file needs to be striped across multiple disks. That's called striping. It's under user control, and you expect parallel IO libraries to take advantage of it. So we'd expect our parallel IO libraries, MPI-IO, HDF5 and NetCDF, to benefit from having striping. And so, okay, that's sample result I don't want to go on to. So we've got plenty of, I'm slightly over time, but I think the most important thing now is, well, I'm happy to take questions. Are there any questions on that? But the main thing is that what we're going to do now is we're going to do the exercise. And so that is on, it is on the GitHub page, okay? And so I've given the first 2 lectures, but the practical, I'm not linked, the exercise sheet's down here, okay? The exercise sheet is based on, so I think what you should do, now, we'll have a coffee break, but before and after the coffee break, familiarize yourself with the exercise. This is the GitHub page for the, whoops, hold on, a different tab. This is the GitHub page for the actual exercise, which has a little README here, tries to explain what it does. But also there's an exercise sheet, which I've recently updated. So I do apologize if there are any errors, but I've updated it significantly. So I will. So I'm looking for. This is the exercise sheet. We'll be using this for the entire. We're using this for the entirety of the exercise of today. So there's some introduction here. So I think the main thing I want you to do just now is to log on to ARCHER2 and get hold of the code, check you can compile it, and check you can run it, and then we'll carry on doing this. But that will be the most important thing you can do. The 2 things you need to note are you need to work in the /work file system. So for you, that's /work/TA128/TA128/ your username. And for today, to ensure fast turnaround, we have a special reservation. But I have a Slurm script called ARCHER2 nov23.job, which will submit the reservation by default. And I can just check that the reservation is working, and it is working because I submitted a job to the reservation. I'll just check. Yeah. So some questions. Okay, very good question. What happens when the OST? So my understanding is that typically the OST is a RAID device, which does stand for redundant array of inexpensive disks, but it's redundant. So typically I think they have 10 disks. So you have 8 disks. So you have 8 disks for your data, but you have a couple of check disks, one of which, so you have a couple of parity checks. So I think that if one of these, definitely if one of these disks fails, of the 10, if one fails, then it can recover it because it has enough information from the parity disk. I think if 2 disks fail, I think you can probably recover as well. But definitely the OSTs are resilient to the failure of one of their constituent disks because there's some parity information there that can reconstruct the data based on the failing of one disk. Does that help? So definitely, if an OST fails, then yes, you lose your data. We do not guarantee, the work file system is not backed up, but in practice, what would happen is one of the constituent, the OSTs themselves are redundant. They would have physically 10 disks in them. The data distributed across all those disks, and then we can recover. I should check. I think we can definitely detect and recover from single bit errors, which means a single disk failing. If double disks fail, I'm not sure, but there is some redundancy there. Does that help, Vanessa? It's a good question. So actually, when I say if you write to a single OST, it's unstriped. From the Lustre point of view, it's unstriped, but physically that data is still stored on multiple disks because even a single storage device now is RAID. On most large-scale servers use RAID arrays. I could find out the details. I'm not exactly sure, but that's the philosophy. So I will. So there's a break now. With just a few minutes behind, but there's a break now until the next. Well, the practical session goes on now to midday. I'll be back. I'm happy to stay around 5 or 10 minutes now. Is anyone having? I'm just interested. If anyone is, I think it'd be good if you try to log. If anyone having any login problems. I mean, so what I want you to do is to go through familiarize yourself with the exercise sheet, which involves reading the exercise sheet and looking at the downloading and looking at the code on the GitHub page. If anyone's having difficulties logging in, yeah. Aaron, how does this resolve mapping to the process in the OSTs? So I don't know what you mean by resolve. So when you create a file, then imagine it's not striped. When you create a file, it's not striped, it's stored on a single OST. And the MDS, the metadata server, will have a lookup table saying where that's stored. If you ask for a striped file, it's stored across multiple OSTs, but all that data is in the MDS. The MDS, the metadata server, knows where all those files are stored. So when you open the file, you go to the metadata server and say, I want to read some data. Where is it stored? And the metadata server says, okay, that's done across these. Then it can work it out. So that's stored in the metadata on the metadata server. Does that make sense? So that's all the information which is stored on the metadata server. So when you open a file, you first contact the metadata server, it tells you where it is, and then you read it. Yeah, okay, yeah, that's a good question. I don't know, Luca, do you know, is it RAID 10? Is it 10? I don't know. Sorry, Luca is assisting here. Luca's an EPCC member of staff. He may know more about it. I don't know what the details of the RAID system are. But the standard thing is RAID 10 disks, which definitely detect and fix a single byte error. Might be able to bit error, sorry. Might be resilient against double failure, I'm not sure.
It should be like done in the hardware. So that's completely transparent to the users.
Yes.
And it's not built into the Lustre, or whether Lustre will be the Lustre network will be resilient in the sense if an ICT fail, it will just be replaced by another one. So that particular file written to that failed OST may not be available, but any new file can still be written. So Lustre is still resistant to failure. It has a lot of redundancy in the network.
But it's important to realize that /work is not backed up. It's not, so it's there. You know, we can't, this is typical of large parallel file systems. Okay, the stuff about Lustre. So the way Lustre works is each OST is actually a Linux file system. If you could log onto the OSTs and list them, you would see every OST has a complete copy of all the files of the whole, files, disk hierarchy file system hierarchy, but it might just be storing. You'd see lots of small files. If you had a big file, and then you were able to log onto the OSTs and list it, there would actually be a separate Linux file system storing a little bit of each file. But so I don't understand. I didn't understand there was any integration. So what we'll do is if anyone's having any problems, logging on, it's hard for me to tell who's logged on, but I definitely know that that there are at least 20 or so I can see that I will actually just share I'll share this. Where are we? So this is me on ARCHER2. Now we are in the TA128 project, and I've called my account. I have sent again, but that's where I am. I'm in /work. Well, actually, by default, we'll end up here in /home. We should really see the /work. But if I can see that there are 1, 2, 3, 4, 5, 10, 15. We have 22 accounts here. So most of you have an account. Difficult for me to tell who's logged on, because that just tells me who's logged on to this node. So if is anyone having any problems logging on, we can sort it. If I find screen sharing, but I would recommend, well, take a break now, but we'll come back for half an hour from 11:30 to 12 to run this exercise. I'm going to take a break, but if you can log in, have a look at the exercise sheet and familiarize yourself with the GitHub page, that should be us up to speed again. So that's so I'm glad so many people got accounts. Actually, that's good. So I will pause the recording.